Good morning. My name is Alex, and I work at Edera. Today, I wanted to share with you how we're using Xen to build a secure container runtime. So a little bit about who we are. Edera was founded last year in the spring by 3 female co-founders. We're a diverse team. There's 20 of us now. We all have different backgrounds, different skill sets, different interests, which I feel makes us a very strong team. We all work remotely. You can see some of us at the last offsite in New York City. We have a pink axolotl mascot named Ivy in the top right. I joined in November, and in the past I completed my PhD in system software, worked in virtualization for both automotive and the data center, and have experience in high performance computing. I tried to summarize our mission as securing container systems by design. I'll get into more why container systems are so important and so broadly used. And 2, to kick ass. And that doesn't mean that we're going to physically harm anyone. It just means that we're going to do the best that we can and have fun while we're doing that. In order for a security system to be adopted, it has to have a high utility, and that comes down to 2 priorities. One is performance and ease of use. If something is really secure but it doesn't perform very well, it's not going to be adopted. And the same thing if it has a lot of friction to be installed and deployed. So let's dive into the area in which we work. Containers. A container is a mixture of kernel resident virtualization mechanisms. Not virtualization in the sense of virtual machines, but in providing subsets of the views of the resources on the system or other applications. So that involves technologies like namespaces or C groups, capabilities, and a few others. These are all implemented inside of the kernel. And the idea is that you want to limit the process view on the platform. For example, what other processes or threads it can see, what CPUs and how much memory it's allowed to use. And in creating a container, you activate and configure some or all of these different technologies together. And that's what it means to be a container. These have become really popular. If you take, for example, running an application on a machine, it will have dependencies on certain libraries existing. And if it's really picky, it'll be certain versions of those libraries. Now, if you extend that to many applications that run on your system, you will have a bundle of libraries and versions and other dependencies that have to exist on the system for the application to be built and run. With containers, we have standards now. You can build an image that contains the application and its dependencies as a deployment now. You can fetch the container image and deploy it with a certain container runtime. This has become really popular in a lot of areas. For example, microservices, CI/CD, and development. So instead of doing make, install, you can do Docker run to build something locally. Most major technology and infrastructure companies use this. Now I'm going to dive into, in the next 2 slides, 2 exploit that demonstrate what we're really going after here. One is in the container environment and one is in the shared kernel. These are called container escapes and allow the application to run its code on the host in root context. The first exploit I want to dive into is called NVIDIA Escape. It's an example of a container exploit. It was discovered by Wiz this year and has a very high severity score because it allows arbitrary code execution on the host in root context. The scenario here is an application that wants to use services provided by a GPU in the system. It'll use the NVIDIA Container Toolkit. The container then has the application, the libraries, and this container toolkit installed. On the host, there's going to be a container runtime that implements certain hooks. We call them OCI hooks, Open Container Initiative hooks. One of them is create container. That runs in root context on the host outside the container to set up the environment so that the application will have access to the GPU and its services. The problem here that was discovered by Wiz is that the environment inside the container is inherited in the context in which the create container hook runs. This is pretty bad. If you think to an example where you run the command sudo, that allows you as a normal user to run a command as the root user. It does not allow certain environment variables to be passed through, notably your path variable, because that would allow running an application you thought you were running to be redirected to some binary that's under the control of the user running sudo. Here, the environment variable ld preload is the root cause of the problem. When you run an application, the dynamic linker will look at this environment variable and preemptively load the file that this environment variable points to. That code can point to something inside the container. If the application writer of the container knows the relative offset to the files in the container, it can then set that environment variable to that path, and then when create container runs, it'll load that and run whatever is in that executable at the time that hook is run. The next example is a kernel exploit. It's called Dirty Pipe. It was discovered a few years ago by Max Kellerman. It has a high severity because it allows an application to overwrite files it doesn't have write access to by exploiting a bug in the kernel through how buffers are managed between the page cache and pipes. So an application that has read access to a file will read it. That will load the data of that file into the page cache in the kernel. Then it will open a pipe and use splice on that and then begin writing the data that it wants to into that buffer in the kernel. And the bug then in the kernel would mistakenly allow writes to go into the file that it read previously in the page cache. And then the file with its modifications in the page cache ends back up on storage. And so with that, you can modify configuration files in the system or libraries or host binaries and so forth. And then the container writer would trigger a behavior in the system that would cause that library or that binary to be loaded, resulting in its own code being executed on the host. Okay? And this is a whole class of exploits that result from having a shared kernel that hosts all the containers that run on the system. So even though I just showed two examples of container escapes, one in the runtime and one in the kernel, there are in fact quite a number that have come up in the last decade and more. On the right I show a list of exploits that have fancy names assigned to them, but there are many more than that that just have CVE numbers. And the takeaway from this is that containers do not contain, to quote one of my colleagues. The misnomer that's been adopted by many in the industry is that they have some kind of hard boundary that protects the host from the application. But that's just simply not true. It's a management interface and not a protection boundary. And this results primarily from a shared kernel attack surface. The scope of this problem is really big. According to recent surveys, 91% of enterprises use Kubernetes. 85% of companies that use some sort of container development method had some sort of cybersecurity incident in the last 12 months. The result of this is that security teams end up chasing down a lot of exploits, running patches, running agents that look for certain things, sending out alerts, and cause these teams and users and frankly a lot of people to feel really frustrated. What can we do about this? Well, we can sandbox an application. One example system, gvisor, intercepts all the syscalls, but our measurements have shown that this is very slow for many different operations. Well, we're at a Xen conference, so we can use virtualization. We can deploy a single virtual machine and move everything inside the virtual machine like shown in the picture. But that means that we have a simulated virtual machine with a full distribution installed. It takes time to boot up. It has a persistent image and state. In this example, what we're only securing actually is the host from the applications in the container. If we're running applications from different customers, they still are exposed to each other if one of them decides to exploit a container escape. So it doesn't really solve the problem. So let's move on to what you should do. Again, let's use virtualization, but let's be a bit smarter about it. What we want to do is to take advantage of the boundaries that virtualization provides. So what we recommend is narrowing the boundary so that inside of each virtual machine we run one container or maybe a set that are related with each other. We also want to minimize the amount of code that gets installed into the VM. Just some support code, no full operating system. Just enough to launch whatever is needed to get the container and its runtime started up. And that'll allow us to optimize for start times and the memory footprint. Then we can move on to running these ephemeral VMs very quickly and in large numbers. This model was demonstrated on Apple machines earlier this year through the Apple Container Framework. Now you can run containers natively on your Apple machine. Container images are fetched and launched inside a virtual machine with a minimal runtime. And that's exactly the model that we're trying to do, except in the enterprise space. And so that's where we step in at Edera. Xen is used as a foundational component in our software stack. I outline a few reasons why we chose Xen on this slide. On our blog, we have 2 write-ups that go into a lot more detail why we made this decision. The first is that Xen is the only open source Type 1 hypervisor design. And that means that it's the first entity that boots up on the hardware. It's in control of the resources on the platform. The memory, the CPUs, the interrupts, and everything else. A Type 2 design is written as a kernel module inside of a host kernel. That means that it relies on the operations and support of the host kernel in order to do what it needs to virtualize guests. It has to ask for time on the CPU to modify page mappings, etc. And because Xen is a Type 1 hypervisor, that means that only implementation that's necessary to support virtualizing guests goes into that component of the software stack, compared to a Type 2 system where the host kernel is much larger because it needs to support a wide range of environments for applications to run. The second reason is that paravirtualization support is a first-class citizen on Xen. That goes beyond paravirtual device implementations like VirtIO to a guest that can boot without virtualization extensions in the CPU. This is what Xen originally supported when it was first released. This means that we don't need a device model like QEMU. We have faster boot times and leaner device stack. All of that goes towards a smaller TCB, or trusted computing base. In other words, the universe of code that supports the application, which must be trusted. Without a device model, and using a Type 1 design, the implementation underneath remains minimal. That takes us from millions of lines of code down to a few 100,000. And the last point is also really encouraging, which is we're seeing increasing use cases where Xen is deployed in safety critical environments. Our system follows the same design that I outlined previously. We package Xen, a set of host systemd services, and the VM resident support binaries together as part of our product. Little components that we have inside of our guests, as well as in the control domain, we cut out and are working towards open sourcing them one by one. One of them is Styrolite, a workload lifecycle manager, and it even has its own IV mascot wearing a Star Trek uniform. Since we don't run guests in the traditional sense, meaning we have a simple kernel and a few support binaries with no persistence, we call this a zone. We're a Rust-first company, and so all of the components that we have, both in the zone and in the control domain, are written in Rust. That means we can't easily take advantage of the implementations like libxl that are in C. And so we've rewritten those components in our stack also in Rust, specifically those parts that make hypercalls into Xen. We additionally have integration with Kubernetes, which is part of the work that goes towards the ease of use, which allows a user to be able to deploy large Kubernetes clusters with very minimal modifications to their configuration scripts. We have quite a bit of ongoing technical work, either in or on top of Xen. For starters, a lot of our focus is on paravirtual guests. That's either PV or PVH. And so we're looking at performance and usability of these types of guests a lot in a lot of our configurations. Another that many of you may have seen on the mailing list, which is bringing up Xen on Azure environments. We also have some folks working on device pass-through, specifically with GPUs and NICs, And we're working together with Stuart and Stefano at AMD, who shared us some initial code patches. We're also experimenting with SRIOV as data center environments take advantage of some of the higher end GPUs that have this on-device support for device virtualization. Some of my work involves providing a VirtIO path for PV guests, on top of which we want to run the file system device. If you recall back to one of the initial slides, I talked about the utility of a security system. One was that it has to have good usability, and the other was good performance. Marina Moore, research scientist at Edera, dug into measurements of our system and made comparisons with other related platforms. The top 3 rows are our system compared with Kata, and the bottom 2 are gvisor and Docker, both of which don't use virtualization. And so we want to make sure that we're comparing related systems in their performance. In both low-level system calls, guest startup times, and higher-level benchmarks like KCBench, which compiles a Linux kernel, and Nginx, which is a web server, we are competitive compared to related systems. In bold, I highlighted the slowest runtime measured for each microbenchmark. In the first column, we notice that gvisor does particularly poorly with some system calls because it intercepts them and emulates them. While other systems have faster startup times, like gvisor and Docker, it's important to note that they don't have the additional work that's involved in starting up a guest. But when compared to Kata, we're much better. When comparing across all systems for the higher level application benchmarks, we remain competitive even with the non-virtualized solutions. We have a white paper that was written jointly between Marina and Alex Zenla, our CTO, which you can find on Archive, and I'll provide a URL to that next. There you can read more about the technical details of the performance analysis as well as some of the details of our design. Lastly, I wanted to share a variety of URLs where you can find more about the work that we're doing. The first is that we have a very actively updated technical blog that goes into detail about the problem space we're working on, the choices we've made, and a lot of other really fun discussions. I encourage you to take a look. We also have a public-facing documentation page where you can continue to find instructions about how to run our code and learn more about how everything's connected. On our GitHub page, we have begun to release some of the components that make up our stack, for example, Styrolite, as I mentioned before, and a security posture benchmarking tool called Am I Isolated? The last link is one to the white paper that Marina and Alex co-wrote, and I hope you all give it a read. Thank you.